Welcome back to our continued discussion on tests of difference, which if you remember from our last video is directly related to testing hypotheses of difference. Just as a quick review from our last video, tests of difference are specifically probing whether statistically significant differences in group averages or means can be found. For the one sample t-test, remember that we're testing whether a specific group mean is different from a known population mean. For the independent samples t-test, you're comparing the means of two independent groups. Independent in the sense that no one person can be in both groups, such as with the case of control and experimental groups. The last test of difference we covered was the paired samples t-test, and this is one you'll use when the scores are dependent or correlated in some ways. We already talked about occasions where this might occur, including in pre-test, post-test experimental designs, in families where the parent score might be correlated within the family units with their children, or a teacher-student pair. I think the best place to start by foregrounding today's discussion is to revisit our last video on t-tests. If you recall from our calculation of t-tests, they're useful when comparing means of groups against each other, but one of the major limitations of the t-test is that it can only accommodate at most one independent variable with two levels or groups. If you have more than one independent variable or one independent variable with more than two levels, you can't use the t-test and must turn to a more versatile, flexible, and slightly more advanced test, the analysis of variance, which we'll be covering today. Today we'll be discussing the analysis of variance, or ANOVA. You can probably already guess that the ANOVA is more versatile than t-tests in that you can compare more than just two means. When specifically would you use an ANOVA? You'd use ANOVAs when you have more than two levels of an independent variable, or if you want to know the relative influence of two or more independent variables with multiple levels each on a single dependent variable. One occasion of when you might use an ANOVA is to determine whether there are differences in desire to engage in telehealth among people of varying education levels, say up to high school, college educated, or graduate school educated. Another occasion of when you might consider an ANOVA is to determine the relative influence of employment status and whether you have a chronic health condition on your support for or concerns of socialized medicine in this country. The point here is that with ANOVA, you can have as many independent variables as your theory permits, and each of those independent variables can have as many groups or levels within them. An important part of ANOVA, which you will come to realize, is that it's based or predicated on a very basic idea. The F statistic of ANOVA is based on a ratio of between group variance and within group variance. Essentially, the higher the between group variance and lower the within group variance, the more likely the F statistic will be significant. What you see in front of you is a hypothetical histogram of a dependent variable. I'll use it to make a point about partitioning variability. The way histograms work is that if several people have the same score on the dependent variable, the column will be higher. Although this is a two-dimensional frontal view of the histogram, it's probably easier to see it from a different angle. This is another view from the top of the histogram, which I'll show you for illustrative purposes only. You can see the total spread of the scores away from the mean, which in this case is represented by the purple bar in the middle, better from this angle. This is what we call the total variation of the scores, which takes into account the distance of each score from the mean. It's similar to variance and the variance equation, which by now you've mastered. The only difference is that variance divides the total spread of scores by n minus 1, whereas total variation does not. The goal of ANOVA is to partition this variation of total spread of scores into the variation that's explained by our groupings versus the variation we can't account for by our groupings, or what we call unexplained variation. As I mentioned before, the more variation we can account for by the groupings of our independent variable, the more likely the independent variable is going to be statistically significant. So you're probably wondering at this point what I mean by variation explained by the groupings of the independent variable versus unexplained variation. You've seen the two sample version of the illustration in front of you already, but here it is with three groups. In this case, the purple line is called the grand mean, and to get that number, you have to sum all the scores on the dependent variable and divide it by the total number of people in the sample. Then, you'll break up the total sample into subgroups based on the characteristics or levels of your independent variable. If your independent variable is income level or socioeconomic status, for example, the blue group might be low income, the green group might be middle income, and the pink group might be high income on some dependent variable such as concern for the economy. Each of these groups will naturally have their own means represented by the vertical colored lines. The between group variation is the total spread of the group means around the grand mean, represented here by adding up the dark purple lines. Each of these groups will also have its own variance, represented here by the orange horizontal lines. The unexplained or within group variation adds up the variances, or average spread of each group's scores around their respective group mean. You may be thinking to yourself at this point, I don't really need to understand this new test. I already know how to do a t-test. In this case, you might think that instead of learning how to do an ANOVA, all you need to do is multiple t-tests instead. For instance, if you have three groups, group A, B, and C, you might just run an independent samples t-test between group A and B, then another between group B and C, and then a final t-test between groups A and C. You could do that, but most reviewers will see that and furrow their eyebrows. The reason being is because we know of something called alpha slippage. If you remember, set alpha is the amount of risk we're willing to take in committing type 1 error when we're running any null hypothesis test. We generally make the assumption that when we compute an inferential statistic, only one test will be performed on a given sample. To be honest, this is a statistical assumption, but it's really never followed. We do, however, try to minimize the number of tests we run on a given dataset, because it is true that the more tests we conduct, the higher the chances are that we'll unknowingly commit type 1 error, a phenomenon known as alpha slippage. If you remember from a previous video that type 1 error, also known as false positives, occurs when you conclude there's a statistically significant difference or association, when in reality that conclusion is wrong. There's a simple formula you can compute to find out how much alpha risk has slipped by running multiple tests on the same dataset, by using the following formula. 1 minus, and in parentheses 1 minus alpha, to the kth power. Here, alpha is usually set for us at 5% or 0.05, and k represents the number of tests you conducted or are planning on conducting. So even if you ran just the 3 independent samples t-tests we discussed in the previous slide among the 3 different groups, our risk of committing type 1 error rises from 5% all the way to 14.3%. For this reason, you have to use statistics that adjust the alpha risk when you want to undertake multiple tests on a dataset. So now that you know why we need to conduct ANOVAs and when to conduct them, let's go ahead and talk about how to compute them. The following is what we call an ANOVA table for one-way ANOVAs. In my opinion, it's really the best way to stay organized so you can come up with the correct statistic at the end. It may seem pretty overwhelming, so you can pause the video now, take some time to digest the different parts, maybe even have a mini breakdown, and feel free to restart it. Okay, let me give you an overview of this table, but know that we'll go over each component a little later. The sum of squares of the independent variable is also called sum of squares between. This represents the between group variation, and you can see from looking at the equation that it calculates the distance of each group's mean from the grand mean. The next component is called sum of squares error or sum of squares within. This represents the within group variation, and it adds up the variance of each group after multiplying each variance by the sample size of each group minus 1. The sum of squares total is the total variation, and if you recall, you get this by summing the distance of each individual score from the grand mean. You also notice that the total variation is equal to the between groups variation plus the within groups variation. The next major component is the mean squares, which we get by taking the averages of the variation. You'll probably notice that mean squares is merely computed by taking the variation or sum of squares of each row and dividing it by its associated degrees of freedom. The final component is the f-value, and this really is the most important statistic on this chart. The f-value is your final statistic, and it will tell you if the group means of your single independent variable are significantly different in some way. You'll notice that the f-value is computed by taking the mean squares between, or in other words, the between group variance, and dividing it by mean squares within, or unexplained variance. Therefore, f truly represents the variance explained by the groupings of the independent variable over the unexplained within group variance. Here's an example of when we might use a one-way ANOVA. You're interested in testing the idea that writing letters to a known other will affect stress levels. For this experiment, you randomly assign participants to one of 3 conditions and ask them to write letters to a friend. In the negative condition, you ask them to write a negative experience they recently had with this friend. In the positive condition, you ask participants to write a good memory they had with this friend. In the neutral condition, you merely ask participants to recall their day-to-day. To measure the dependent variable stress, you took a swab of their saliva and sent it to a lab to check participants' level of cortisol, a biological marker of stress. The more the cortisol, the more stressed participants were. Here are your data. The alternative hypothesis that you're proposing is that the average cortisol of the negative letter writing group was larger than the neutral group, which was larger than the positive group. The null hypothesis you're testing is that the average cortisol level across the groups were equal. To begin calculating the one-way ANOVA, we need to start by calculating the grand mean, which is represented by an X with 2 lines above it. The calculation for the grand mean in this problem is very simple. We simply take an average of the 3 group means. The means of the 3 groups were 9.0, 7.0, and 5.5. So we add those numbers and divide the sum by 3, giving us 7.17. In step 2, we compute the between group variation or sum of squares between. Between group variation is equal to each respective group sample size multiplied by the group mean minus the grand mean squared. So 11 represents the sample size of the negative letter writing group. 9 here represents its group mean. 7.17 is the grand mean we just computed in step 1, and we square the difference in the parentheses. We do that for all 3 groups, and then add those products together to get us a sum of squares between of 62.23. In step 3, we must find the within group variation. The equation for within group variation tells us that we must multiply each respective group sample size minus 1 and its variance, and then add these products up. So 10 represents the sample size minus 1 of the negative letter writing group, and 3.5 represents that group's variance. You do that for all three groups, sum the products, and that gets you a sum of squares within of 82. As I mentioned earlier, sum of squares total is equal to sum of squares between plus sum of squares within. So we add the between group variation, which we calculated in step 2, to the within group variation, which we calculated in step 3, to give us a sum of squares total of 144.23. In step 5, we calculate the degrees of freedom for the sum of squares between, sum of squares within, and sum of squares total. The degrees of freedom for the total variation is calculated by the equation total sample size minus 1. Because we had 30 participants across 3 groups, our n is 30, and the resulting degrees of freedom is 29. The calculation for the degrees of freedom for the between group variation is k, which represents the number of groups or levels of the independent variable, minus 1. So because we had 3 different groups, the negative, neutral, and positive condition, our k is 3, which makes the degrees of freedom between 2. The degrees of freedom within is computed by taking the total sample size and subtracting it from the number of levels of the independent variable k. So here, 30 total participants minus 3 groupings of the independent variable gives us a degrees of freedom within of 27. You should make sure that the degrees of freedom between and the degrees of freedom within add up to the degrees of freedom total. In step 6, we divide the sum of squares between and the degrees of freedom between to get our mean squares between of 31.12. We also calculate our within group variance, or mean squares within, with the calculation sum of squares within divided by degrees of freedom within to get us to 3.04. Our final step before applying our decision rule is to find the F statistic. F is found by taking the mean squares between and dividing it by the mean squares within, which is found in step 6. Our final F value here is 10.24. We can now create a decision rule and a final conclusion about our calculated F statistic. This F distribution table is helpful because it's the specific case of a set alpha of 0.05. You do need 2 pieces of information, however, to find the correct critical F value. You need the degrees of freedom between, which is the numerator degrees of freedom, and the degrees of freedom within, which is the denominator degrees of freedom. If you recall from step 5, our degrees of freedom between was 2.0, and our degrees of freedom within was 27. So the intersecting point is a value of 3.3541, which is our critical F value. Now we have all necessary components to make a decision rule and a final conclusion. Because our obtained F of 10.24 is larger in absolute value than the critical value of 3.35, we reject the null hypothesis. By rejecting the null hypothesis, we can conclude that the mean stress levels of the 3 manipulated groups significantly differed from each other in some way. But what does "in some way" mean? We'll explore that in the coming section. You heard me say in the last segment that the means of the three groups differ in some way. What does in some way mean? Well, it means that there's a significant difference between at least two groups of the independent variable, but it doesn't specify which groups. That's because the F statistic is what we call an omnibus test. As an omnibus test, the F statistic provides an overall result that signals if there's something worthy of further probing or whether there's nothing there. A non-significant statistic indicates that all the means of the independent variable are equal, so we should just stop there and call it a day. A significant F value signals that at least one meaningful difference exists somewhere among the groups, but it doesn't tell us exactly where. To do further probing when you have a statistically significant F value, you must use what we call post hoc comparisons. There are admittedly a bunch of different comparisons available to you, and all are a little different. We won't go into detail about the different ones, but it is usually best to find a post hoc comparison that balances type 1 and type 2 error risk. The Tukey's test or the Chaffee's test are fairly common choices for managing type 1 and type 2 errors. Here's an interesting use of ANOVA when you have a prior reason for thinking that your group means will be distributed in a specific pattern. For example, we might have proposed that the mean cortisol level for the positive letter writing group was going to be the lowest, the neutral group was going to be somewhere in the middle, and the negative letter writing group was going to have the highest mean cortisol level. So the distribution of the means represented by the circles, with each group standard deviations represented by the bars around the circle, could have been arranged like this. If the orange dotted line can travel through the means like this, we refer to the arrangement as a linear trend. If the means are arranged to look something like this, where there's a single knot or turn in them, it's called a quadratic trend. Two turns or knots, as seen here, is what is called a cubic trend. And the quartic trend has 3 knots. The broader point that I want you to understand and take away is that these polynomial trends in ANOVA can be tested so long as you have some a priori theoretical justification for testing them. Now that we talked about the one-way ANOVA, which accommodates one independent variable with as many levels or groups as you wish to test, we'll move on to a more versatile test of differences where we can include multiple independent variables called factorial ANOVA. As you probably already guessed, for factorial ANOVAs like one-way ANOVAs, you must have categorical or nominal level independent variables and a continuous dependent variable. Here are a couple of points that I wanted to make about factorial ANOVAs before moving forward. We refer to factorial ANOVAs as blank-way ANOVAs, where we substitute blank for the number of independent variables that ANOVA is testing. For instance, a three-way ANOVA is testing 3 different independent variables, whereas 5-way ANOVA has 5 different independent variables. In our report, we refer to ANOVAs as blank by blank by blank ANOVAs, substituting the blank here for the number of groups for each independent variable. So if I'm looking at age, children and adults, and gender, males, females, and transgender, as my primary independent variables, I would have a 2 by 3 ANOVA. Factorial ANOVAs identify pretty much the same thing as one-way ANOVAs. That is, it'll tell you differences among groups for each independent variable. But it can also identify what we call moderations or interaction effects. Moderation occurs when differences in the dependent variable between or among groups of one independent variable depend on the third variable. I'll explain more about this later in this video. A moderating variable means that the differences between groups or levels of one independent variable are unique or specific to the levels of another independent variable. So, for example, we might expect to see differences in the amount of verbal aggression between males and females, but only within adult groups, and these differences disappear in children groups. The point here is that moderating variables can usually be identified when an answer to a scientific question about the relationship between two variables is, well, it depends. For instance, I was once asked whether people who are mistrusting of their partners are more likely to engage in online surveillance versus those who trust their partners. My answer was, of course, well, it depends. The reason why is because the answer was not so straightforward. I proposed that mistrusting people survey their partners online more than trusting partners when these individuals made significant relational investments such as time, shared living spaces, and shared social networks toward their relationship. At low levels of investment and commitment, there were no differences because presumably surveillance was low regardless of whether partners trusted or mistrusted their romantic others. This is an example of an it depends relationship that is indicative of a moderating variable. The bar graph in front of you depicts what I mean by interaction effects or moderation. Here, the independent variables were self-esteem, measured as low and high, and biological sex, males in blue and females in red. The dependent variable is one's intent to divorce his or her current spouse. Pause the video here and see if you can make sense of what this bar graph is saying. The interpretation of this moderation is as such. Sex moderates the relationship between self-esteem and intent to divorce in marital relationships, such that at low self-esteem, females intend to divorce their spouses more than males. But this difference appears to flip at high levels of self-esteem, wherein males intend to divorce their spouses more than females. This is an example of an interaction effect. This is yet another way to look at both main effects and interaction effects using a line graph. In the figure in front of you, the diamonds reflect the means for each group. Here are the hypothetical data for a study where I looked at different companies to see whether their social media posts influenced customer engagement. The two independent variables were quantity of posts, low number of posts and high number of posts, and specific platforms on which these posts were made, Facebook or Twitter. Customer engagement was measured by the number of responses or likes garnered by customers. Here are the hypothetical arrangements of the data. In this first arrangement, you can see that there's no significant difference for posts, but there is a significant difference for customer engagement for platforms. The best way to visualize this is to think about what would happen if social media platforms weren't taken into consideration. Then customer engagement for the low number of posts and the high number of posts would practically be the same. Here's an example of when we have a main effect for number of posts, but no main effect for social media platforms. The third arrangement is an example of an interaction effect because the data are telling us that the differences between number of posts on customer engagement depend on social media platform. For Twitter, the number of posts does not influence customer engagement, but for Facebook, high number of posts seem to engage customers significantly more than low number of posts. Because these differences depend on social media platforms, this is an example of an interaction effect. Also, you'll notice that the lines never cross or intersect. Because they don't, we call this an ordinal interaction. The last image here is of a disordinal or crossover interaction. You can see intervening differences specific to social media platforms. For Twitter, customer engagement is higher with lower numbers of company posts than higher posts. But for Facebook, these differences are exactly the opposite. Customers seem to be more engaged with higher numbers of company posts than with lower posts. This is yet another example of an interaction effect. So let's try to calculate a two-way ANOVA. Remember that two-way ANOVAs mean that I have two independent variables. What you see in front of you is called a factorial ANOVA table. It looks pretty much identical to the one-way ANOVA table with the addition of the interaction term. Additionally, we won't use the term between groups any further because we have more than one independent variable. So instead, we use the term rows and columns to represent how the summary data are presented. The sum of squares, degrees of freedom, mean squares, and f-statistic for the first and second independent variables are practically the same as the one-way ANOVA. The f-statistical for variable A and the f-statistic for variable B tell us whether there's a main effect for either independent variable. The main difference here is the test of the interaction effect. The sum of squares for the interaction between variables A and variable B is calculated by taking the mean of a specific cell, subtracting that cell's row mean and column mean, and adding the grand mean, squaring that result and multiplying it by the sample size of that cell. The degrees of freedom are calculated by multiplying the degrees of freedom for variable A and the degrees of freedom for variable B together. We'll go over each component piece by piece in the following example. Here's an example of a problem in which you might use factorial ANOVA. You're interested in examining the relationship between age and cultural orientation in the use of avoidant conflict management styles. You had 84 participants evenly distributed among your cells in a 2x2 factorial design. We're using factorial ANOVA because we had two nominal level independent variables, age broken up by children and adults, and people of two different cultural orientations, individualists and collectivists. You also want to see if age moderates any differences in avoidant conflict management styles between the two cultural orientations. It's important to note that there are three hypotheses being simultaneously tested here, which correspond to the three f-statistics we'll get from our factorial ANOVA table. They are the hypothesis of a main effect for age, a main effect for cultural orientation, and an interaction effect. So here are the steps for calculating the factorial ANOVA. We begin in our first step by calculating the averages of the means for the rows and the columns. Here are the equations for calculating these averages. For example, to find the average of row 1, we take the mean of row 1 column 1 and add it to the mean of row 1 column 2 and divide that by 2 to get 27. We do the same for row 2. We then compute an average for each column. Again, we add the mean of column 1 row 1 to the mean of the cell in column 1 row 2 and divide by 2 to get a column 1 average of 33. We do the exact same thing for column 2. Then, in our next step, we calculate the grand mean by finding the averages of the row means we calculated in step 1. So 27, the average of row 1, plus 31, the average of row 2, divided by 2 is equal to 29. Therefore, our grand mean here is 29. In our next steps, we calculate our main effects. Remember, the main effects tell us whether the two levels of either independent variable are significantly different from each other. In step 3, we calculate whether there's a main effect for age. Here's the equation to find the between group variation for age. As you can see, you take the row averages, subtract it from the grand mean, square that difference, and multiply the product by the total number of participants in each row. In the case of the sample size for, say, row 1, you have 21 participants in row 1 column 1 and 21 participants in row 1 column 2. So your n for row 1 is 42. Doing all the basic arithmetic will give you a sum of squares row, which represents age, of 336. In step 2, you do the identical calculations, but this time for column averages representing cultural orientation. Again, you take the column mean for individualists, subtract it from the grand mean, square that difference, and multiply it by the column sample size of 42. You do the exact same thing for collectivists. Doing all the basic arithmetic will give you a sum of squares column, which represents cultural orientation of 1,344. In step 5, we calculate the variation for the interaction effect. Here's the equation for calculating that interaction. As you can see from the calculation, you take the mean of each cell, subtract it from its respective row mean and column mean, add the grand mean, square that number, and multiply it by its sample size. For example, for row 1, column 1, which represents individualist children, you would take the mean of the cell, 30, subtract the row average of 27 and the column average of 33, and add the grand mean of 29. You would then multiply that resulting value by 21, the sample size for that cell. For individualist adults, you start with the cell mean of 36, subtract the respective row mean of 31 and the column mean of 33, and add the grand mean of 29. Square that result and multiply it by the cell sample size of 21. By doing the basic arithmetic, you get the sum of squares interaction of 84. In step 6, we calculate the within group or unexplained variation. We do this by multiplying the variance of each cell by that cell's sample size minus 1 and add those products together. Again, doing the basic arithmetic, we get sum of squares within or unexplained variation of 3,200. So now that we've calculated all of the sum of squares for age, culture, the interaction, and within groups variation, we can complete the remaining parts of our two-way ANOVA table. Remember that sum of squares total is the sum of all other components of variation. So we can add the sum of squares age, sum of squares culture, sum of squares interaction between age and culture, and the sum of squares within to get a sum of squares total of 4,964. The degrees of freedom for age is represented by the equation number of rows minus 1. Here we had 2 rows, children and adults, so our degrees of freedom is 1. The calculation for degrees of freedom for culture is number of columns minus 1. Because we had 2 columns for 2 cultural orientations, our degrees of freedom is 1. The degrees of freedom for the interaction is calculated by multiplying the degrees of freedom for age and the degrees of freedom for culture. So 1 times 1 is equal to 1. The total degrees of freedom is calculated by the total sample size, 84, minus 1. We calculate degrees of freedom for unexplained variance by taking the total degrees of freedom and subtracting the degrees of freedom for age, culture, and the interaction term to give us degrees of freedom within of 80. The next step is to calculate the mean squares for age, culture, the interaction, and within group variance. Recall that the mean squares is calculated by taking the sum of squares for that line and dividing it by the degrees of freedom for that line. We do this for all lines except for total. The last step is to calculate the F value for our 3 null hypotheses. The F value represents the variance explained by the between group variance or interaction over the unexplained variance. So for the first line, F equals mean square age over mean square within. We also do that for culture and the interaction term to give us our final F statistics. The penultimate step before implementing our decision rules is to look up our critical values. You should be aware that you may have a different critical value for each of your different F statistics. For this 2x2 example, however, all critical values will be the same, with a numerator degrees of freedom of 1 and a denominator degrees of freedom of 80. The intersecting critical value for all three hypothesis tests is 4.00. As you're probably already aware, the final step is to apply the decision rules we've carried over to determine whether or not we can reject each of the three null hypotheses being tested. For age, because the calculated F value of 8.4 is higher than the critical value of 4.0, we can reject the null hypothesis and claim there's a main effect. For cultural orientation, because the calculated F value of 33.60 is higher than our critical value of 4.0, we can also reject the null and conclude there's a main effect for culture. For the interaction, because our calculated F statistic of 2.1 falls below the critical value of 4.0, we fail to reject this null hypothesis. Unfortunately, there's no interaction effect. Pause the video here and see how I would write up the results section for this ANOVA test in a research report. That's pretty much all I have for ANOVAs and tests of difference. We covered a lot today, so if you made it up to this point in the video, great work. Remember that we learned about alpha slippage and why we want to avoid multiple unnecessary tests on the same dataset. We went over the one-way ANOVA, which is used when we want to compare 3 or more group means against each other. We learned about what it means to say that the F statistic is an omnibus test, and how further probing in the form of post hoc comparisons is needed when we have a significant F value. Finally, we learned when we would use a factorial ANOVA and how to calculate it. You may need to go through this video a couple more times to get a handle of the calculations, but I know you can do it. As usual, if you have any questions, you can email me or drop a question in the comment section below. Peace out.